All right, class. So I'll start with the revision of electrostats today. Electric field and charges. First, I'll discuss the theory part. We'll practice some questions. Then we'll practice we'll see the theory part of electric potential and capacitance. And then we'll practice some questions from there. Now, C class, otherwise also no, from the weekend classes, you will be getting sufficient time now. Weekdays are also available and even the weekends are also available. You can text the topic with which you are having doubt the entire month Feb before your boards are actually starting. So in whichever topic you have doubt, no, any specific topic, any specific question, like suppose let's say one student has doubt in what are the properties of electric charge. So you can just text me properties of electric charge doubt. So I'll take your class accordingly whenever you are available, whether it's a weekday, whether it's weekend, whatever you prefer. So start practicing and keep collecting your doubts. If you have doubts, we'll arrange classes for you. Special doubt classes are there. Now, yes, so electric field and charges. Here the first concept comes of electric charge. I'll keep telling you what all things are important. So if you want, you can note it down as well. So from electric charge, you barely have certain questions coming. Two types of charges exist, positive and negative charge. Now from here, you have to remember the SI unit of electric charge and this value 1.6 into 10 to the power minus 19 coulombs. This value is important to remember because you have seen till semiconductor last lesson. Even when we were doing the last lesson, what happened? This value got used 1.6 into 10 to the power minus 19. So this is the electronic charge value of the electronic charge value. So this value you have to remember, and this is equal for proton and this is equal for electron. Both the values are equal for both of them. So charge on electron you have to remember. Then this doesn't come how to make the atom neutral. From here, you have the methods of charging. Now see, even from the methods of charging, you have certain important topics. From methods of charging, questions, numericals come from charging by friction and charging by conduction. From charging by induction, you will be having just theoretical question. How charging by friction? See, you will be just getting, see here, how will you get it? We did certain questions also. When electron moves, we have seen that, and I have told you this before as well, when electrons and protons are there present. So protons are present in the nucleus and these are held through tight nuclear forces. These are very strong, tight nuclear forces. While the electrons which are revolving around the nucleus, these are held through electrostatic forces, weak Coulombic forces, electrostatic force of attraction. So these are weak in comparison, right? These are weak. So what happens? Since these electrons are held weak and protons are held so tightly in the nucleus, electrons easily get detached, right? Electrons are the ones that are actually transferring. It's not the transfer of proton that occurs. It's actually the transfer of electrons that occurs. So electrons actually get moved from one atom to another atom. That is how the charging takes place. So this method of transferring of electron is basically known as charging. So questions can come as in what type of charges have traveled or why does only electron has traveled, right? So questions like this can be asked. Apart from this, you have this question from conduction mainly, which I wanted to tell you more than friction. Friction you will be able to manage. In charging by conduction, just remember when two bodies are there, they are placed in contact with each other, they'll get charged because of this transfer of electron occurring only. Now remember, if the bodies are identical, charge distribution will also be identical. Let's say this is having 4 electrons, this is having 0 electrons, so it will donate its 2 electron here. Until and unless both have equal charges. Fine, until and unless both the bodies have equal charges. So 4e and here 0, no electronic charge. So when both these bodies are placed in contact, one will be developing 2 electronic charge, second body will also be developing 2 electronic charge. So this is charging by conduction. From here, you get the numericals, such as numericals like these. If two bodies are there, they are kept beside each other. Third, identical uncharged sphere is kept. So when that uncharged identical sphere is kept, what happens is that with which it is making the contact, same thing will occur. Divide the charge, add the charges and divide it by 2 to get amount of charge distributed. Fine, because it will reduce the values of force. I think in one of your mock tests also this question has come. Then charging by induction. See, in charging by induction, what do we do? In charging by induction, we take a rod, a glass rod, and we charge it with one of the charges which we want. Let's say I have charged it with positive. Here in this example, I have charged it with positive. This was initially neutral, having equal amount of positive and negative charges. Initially, it was neutral. Now, as soon as I'll bring a positively charged rod towards the periphery of this glass slab which I have, what will happen? All the positive charges will attract all the negative charges. So all the negative charges will get accumulated at one place while the rest of the portion will remain neutral. So slowly and slowly what will happen? Entire negative charge will be accumulated at the first end and all the positive charges will be left at opposite end because of repulsion of a positive charge you can see, or because of attraction of negative charge you can say. Both these things. This will happen. Now, this is just what is meant by charging by induction. But how do questions come? If the question will say, make the body completely, let's say, positive. Or I think I had shared a question as well with you. So if a body is given to you, just a second. Yes, see over here. Now here what will happen? You have got to make the sphere completely positive. So one thing is that we'll bring a negative glass rod with us. So what will happen? All the positive charges will get accumulated at one end and all the negative charges will be left at the opposite end. Now I have this till the time, remember, always remember, induction is temporary electrification. It means till the time I'll be holding this glass rod, no, then only these charges will be separated. As soon as this glass rod is removed, as soon as I remove this glass rod, they'll become, all the positive and negative charges will nullify each other and it will become back to neutral. So what do I have to do? Meanwhile, I'm holding this rod, I can earth it. So when I earth it, all the negative charges will drain into the earth. That's how, no, what is meant by earthing. So now what is there? Even if I remove the rod, this is left, this part is left with me. Now, even if I remove the rod, the positive charges will spread evenly. So this is how the application based questions from induction come. So like this only, you have to remember all of these. Just the definition part, just basic definition. This you can explain in your words as well. Then you have Coulomb's law. Coulomb's law says what? See, two charges are there. Both the charges are separated by a certain distance. Any two charges exist. This is, let's say, Q1. This is, let's say, Q2. Any two charges exist. So according to Coulomb's law, what will happen? The force of attraction that is existing between these two charges, This force of attraction is directly proportional to one thing, that is the product of magnitude of these charges. If this magnitude is Q1, magnitude is Q2. So product of magnitude will be Q1 into Q2 and inversely proportional to square of distance between them. So when you combine this entirely, you get the formula F is equal to KQ1 Q2 by R square. Here the constant that we use is 1 over 4 pi epsilon. This is the constant that we use, whose value is 9 into 10 to the power 9. Then epsilon and epsilon naught, basically these are absolute permittivity. This governs dependency of the force on medium. Suppose I have two charges kept in air, I am getting a certain value of force, and as soon as I keep those two charges in water, I'm seeing there's a difference. As soon as I'm keeping the two charges in glass, there's a difference in the force. As soon as I'm changing the medium, I'm keeping the two charges in oil, I'm seeing another difference. So all these combined together, when you will combine all these together, it means you can directly conclude the fact that change in the medium is producing change in the force, right? Any change in medium is producing any type of change in force. So that change that is occurring, how much change will occur when you will change a medium? How much change should decrease? How much change should increase? All these values, this is governed by permittivity. So permittivity of free space, that is air, you have to remember this is 8.85 into 10 to the power minus 12. Then you have basic properties for it, and this is Coulomb's law. This is important. Some students were asking questions for Viva also. So see, from Viva perspective also, you get such kinds of question to write on the spot, whether it's because it becomes very confusing when you're writing no k, the constant k is epsilon over epsilon naught, or was it epsilon naught by epsilon. This becomes confusing. So always remember, this is epsilon of medium by epsilon naught. But when you will write k, k will be force in air by force in medium. Fine. Epsilon by epsilon naught. Epsilon in medium by epsilon in air. But when you will write force, it will be force in air above, then force in any medium below in the denominator. Then we have the concept of electric field. Just understand the concept of electric field. Here in the case of electric field, you will be having a source charge. This, we call this as a source charge because you can see here this is producing a certain type of space around itself. Now what is happening to this space? We have brought another charge. This charge is also having its own particular space. I have brought this closer, nothing is happening. I have brought it closer, nothing is happening. When I bring this charge at this position, as soon as their electric fields coincide with each other, or this small q enters the area or the vicinity of the source charge, I'm feeling slight forces of repulsion. I feel the charge is moving away. It wasn't moving away when it was covering the entire part, but as soon as it is bringing close, I have brought it closer to the source charge, it is moving away. So that space which is created around every individual charge, this space that is created where you can feel the forces of attraction or you can feel the forces of repulsion, this field is known as electric field. Simply, this is known as electric field. So the concept of source charge is there, test charge is there. Then when you divide it by the charge, no, force per unit charge, you can say, or you can, one more definition you can have for electric field, it is the amount of force for 1 coulomb of charge. Why? Because the formula of electric field is force per unit charge. Formula of electric field is force per unit charge. That's why we write the unit as Newton per coulomb. We also have one more unit, that is volt per meter, but we'll see that differently in the next lesson. So E is equal to KQ by R square. What was force? Force was KQ square by R square. See, this is force, KQ square by R square. Electric field, remove one charge from here, it becomes KQ by R square. That's electric field. Remove the radius as well. So that becomes KQ by R, that is potential. So this is how you can basically remember merely the three formulas which you have, basic formula. So force is KQ square by R square, electric field is KQ by R square, and potential is KQ by R. This is how you can remember all these. Apart from this, depending on the questions, you have different formulas. Then one more thing, the electric field's direction for a positive charge will always be away from the charge. And that's how you even identify electric field lines as well. So whenever you see electric field lines or forces of attraction or repulsion, these are moving away from the charge, completely moving away from the charge. You'll directly name that the charge is positive, and this occurs in only in positive charges. Whereas for negative charges, all the rays, electric field lines, electric field rays, these will be moving towards the charge. So electric field moves in opposite direction or away, not opposite, but away from the charge in positive charges, and it moves towards the charge for negative charge. So away for positive, towards for negative. Fine. Then from electric field, see, superposition principle is what? Whenever we have superposition principle basically means that I have Q1 and I have this point P, so I can find out electric field KQ1 by R1 square. Right, I have electric field, I have charge, I can find it out. Then secondly, I have Q2, I am having this point P, I can find out E2 as well. I'm having third charge, it will be also having a certain separation, so electric field third also exists. So likewise, you have 4th, 5th, 6th, 7th, 8th, 9th, 10th, and nth number of charges are there. Now, how will I get the net electric field? I'm not asking to write about individual Q1 electric field or Q2's electric field. Right, now I'm not asking that. I want one complete answer. I want to know what is the net electric field on P point, whether it's from Q1, whether it's from Q2, be it any charge. So what will I do? I'll apply superposition principle. Calculate every electric field individually. Calculate E1 individually. Calculate E2 individually. Calculate E3 individually. Calculate E10 individually. Ultimately, calculate Enth individually. And whatever answer you get, that will be the net electric field. But one problem is there, that electric field is not a scalar quantity. It's a vector quantity. It requires direction. Electric field requires direction. So we'll not be directly adding it algebraically. All these individual values which we are getting for the electric fields, we'll be adding it vectorically, because electric field is not a scalar quantity. Then from this, just remember one thing: potential electric field force. Any quantity you talk, if it's a symmetrical figure at the center, that quantity will be 0. From here, see, you do not have much from here. Electric field, then dipole moment we have. Yeah. So see, magnetic monopoles we had seen recently. Remember, I told you magnetic monopoles do not exist. So similarly, electric monopole is also there. Electric dipole is also there. Monopole means system having a single charge. So like if I say a body is made up of electrons only, entirely electrons, so it is believable. Definitely electrons do exist independently. Or if I say one proton is there or one electron has traveled, so that is believable. One electron can travel. But when I talk about magnets, if I say this magnet is just having north part, north polarity, there is no south polarity. South polarity I have separately. That is not possible because magnetic monopoles do not exist. Always an association with a north pole, at the opposite end you will be having a south pole. Now electric monopoles exist. Now what is electric dipole? And magnetic dipole is also similar to this only. Two charges, they are having the same magnitude. It means, let's say if I talk about 3 microcoulomb. So one charge will be having 3 microcoulomb, another charge will be also having 3 microcoulomb. Difference will arise in their charges. One will be positive, other will be negative. And they will be separated by a small separation. This is what is meant by dipole. So a system having equal amount of positive and negative charges at a small separation, this is known as a dipole. How do we calculate it? Take the magnitude of any of the charges. See, magnitude is same for both the charges. So take any value and multiply it with the separation. So SI unit also, this is coulomb. For distance, it's meter. It will be coulomb meter. This is what is meant by electric field and dipole. Now, these derivations are important class. Electric field on axial line on electric dipole and electric field on the equatorial line of the dipole. These two are important, and in some papers I have seen in one set it is given calculate electric field on the axial line of electric dipole, and in another set it is given electric field on equatorial line. Like this also it is given. In one set it is mentioned as axial line, in another set it is mentioned as equatorial line. So be prepared for this. See the derivation thoroughly. Remember the final formula. But when you're using ideal dipole approximation, no, Fahad, not necessarily. See, in your examination, no board examination, every year number of sets change. Sometimes there are 5 sets as well. A, B, C, D, E. 5 sets also are there. But mostly it happens that the question numbering is different. Like for you, let's say we both are giving exam. So what is question number 1 for me might be question number 8 for you. That can exist. So questions are shuffled also most of the times with 1 or 2 additional questions. Like in my paper, axial line on dipole is asked, in your paper, equatorial is asked, but rest of the paper is same with shuffling of questions. No chance for copying. No, Fahad, no chance for copying. You have sufficient time. All right. So see, electric field, and one more thing, if you are caught copying, then there are no chances of saving also, Fahad. No chance of for copying, otherwise no chances for saving. Nobody is going to save you over there. And 2 sets also can be there. Sometimes 2 sets are also there in board examination. So yes, in electric field, axial part, you have 2 kpr by r square minus a square to the power whole square. Now, class, this formula is there, and one ideal dipole approximation is also there, which is 2 kp by r cube. Now, class, do not blindly use this formula, 2 kp by r cube. Right, do not use this directly, because in some questions this is asked, this is demanded to write. When you have to use this formula, when you have to use other formula is depending on this condition. If you really think that the size of dipole is very small, how to compare this? How to compare this? Suppose, let's say the size of dipole, this 2a that we write, separation between dipole, this is given as 3 millimeters, right? Very small amount. And the r's value, that is from the center of the dipole to the point of calculation that we take r, this is given as 3 meter. So you can see a huge amount of difference. 3 is very much greater. 3 meter is quite greater than 3 millimeters. So there you can use dipole approximation. So it's not like questions on this do not come. Questions are there which demand this formula as well. So that's why I'm saying be careful when you're using the form. Same goes for axial. Axial derivations are more often asked in the paper than, equatorial derivations are more often asked in the paper than axial electric fields. So electric field on equatorial line, because here you involve no proper vectors are also there. So usage of electric field, how are they related to vectors? These are also asked. But this is just probability thing. Both can be asked to you, any of these. Fine. So this is a basic just comparison between both of them. Axial line is 2 kp by r cube. This equatorial line is minus kp by r cube. For direction of axial line, whatever is the direction of dipole moment, you will put exactly that direction for axial field. Whatever direction is that for equatorial line, you will put it exactly opposite to it. Suppose, let's say, direction of dipole is from negative charge to the positive charge. This is the direction that is coming. Let me make it clear. Let's say properly, this is from towards the right, from left to right. This is the direction. So if I'm talking about axial lines, direction will be for me also in axial line, it will become I cap only. But if I'm talking about equatorial line, my direction will become minus I cap. So depending on the direction of dipole moment, you take out the direction. And this also comes class in the MCQ part. No, this can be asked to you. E axial is equal to 2 times the equatorial. This you can take the ratio and see up there. Fine class. This is, then you have torque. C class from torque. No, basically in torque, you just have to remember few basic things you have to remember in torque. From axial line, if you're asking, see, axial and equatorial line, they are separate. That is separate. Combining both of them in a single question is a very tedious task. No, you don't have 10 markers in your physics exam. You will be getting the case-based study also. Maximum 4 marks question will be there. So entire derivation in one single question is not fine. That won't come. One single question that won't come, but you cannot decide which derivation is coming, which is not coming, either of them is coming or both of them are not coming. That you cannot predict. Fine. So that nobody can predict. That's why prepare at least all the derivations and formulas with you. At least all the derivations class. I think you all have sufficient time still now as well. So what you can do is write down all the derivations separately so that at the last moment you can revise all the derivations. I think important derivations are sent on the group as well. Now from here, this part is also good and important class. This is just involves your basics of kinematics, which you study in class 11. Very basics of kinematics. Fine, so that can be involved. And rest of your physics, F is equal to QE. So electric, you have acceleration is force by mass. So you can write the value of force as QE. If it's an electron, you'll put EE by M. Mass will be depending, whatever you have, this you can use, but basic equations, S is equal to UT plus half AT square, V is equal to U plus AT, V square minus U square is equal to 2AS. These three equations can be easily used. Fine, basics of kinematics will come, not difficult portions. Fine. Now see, torque's derivation is important class, and torque's derivation have been coming in the exam. So in torque, here what we'll do, whenever class, I am repeating this, when I was teaching you all also this lesson, I had told you that time also, whenever you are asked to write down the derivation of torque, if derivation of torque comes, do not directly start away with the derivation of torque. Mention this fact that net force on the dipole is 0. Mention this fact. Show that plus QE is cancelling minus QE. No translatory forces are there. Why am I saying? Because if this was existing, you wouldn't have got torque using this derivation. So mention this, that yes, net force on a dipole is 0. Plus Q is cancelling minus QE. So you have no translational motion, translational equilibrium exists, but rotational equilibrium does not exist. So you are having torque in your system. Now how to calculate torque? Force into the perpendicular distance. Force is QE, charge multiplied by electric field, and separation, perpendicular separation is C. Just drop it. This is the angle inclined dipole that you took. No, just drop a perpendicular to the surface in which you are calculating. You will get it as 2a sine theta, normal using simple trigonometry if you apply. So the entire formula will become T is equal to P cross C, that is PE sine theta, right? So work of torque is what? It wants to rotate the dipole and align it in the direction of electric field. This is what is meant by this. These are very easy to guess and write. So what you can do is remember the angles and the conclusions. How questions can be asked from this? It won't be directly write the dipole, write the electric field when dipole is parallel, or write the torque when dipole is parallel. No, questions will not be like this. How questions will be, state the condition of stable equilibrium like this. So you will show when the dipole is parallel to electric field, theta becomes 0. Since theta is 0, this net force is also 0 here. Torque is also 0 here. So PE sine theta is 0. That's why, since torque is also 0 and force is all, that's why I'm saying mentioning translational force is important. Why? When translational force is 0, and the rotational force is 0, rotational force means torque, then only you're getting the final condition of stable equilibrium. So mention net force as 0 and net torque as 0 for complete condition of stable equilibrium. When they are kept parallel to each other, then also it will be 0. But problem is that it will be unstable equilibrium. So how to identify? Both are having angle as 0. Both are having net force and net torque as 0. So both of them should be same. Both of them should have been same. So how does the difference arises? Whether you are able to shift your dipole back to its mean position or not. Like in the previous one. Here. If you release the torque, that is rotating it, it will move like this. And it will attain its original position that it was having. Fine. So that's why when the original position is received by the patient, is achieved by the patient, by the dipole, when the exact position is achieved by the dipole, you will call it as stable equilibrium. But when the dipole is not able to achieve its position back, see here, like this. In this case, what is happening? It has been inclined. Now when you release it, it will move here. This will be the path of it. Oh, when the torque will be released from here. This will be the path of it. So now what will happen? Since the path is this, the original dipole position wasn't like this. Original dipole position was to align it. So this is your target. When you receive this, then you get stable condition. So both are in equilibrium, but one is stable, one is unstable. So you have to identify by yourself whether it's stable or unstable, right? And when the question says write the condition when dipole is maximum, when the torque is maximum, so you will say when the dipole is perpendicular to electric field, the torque is maximum. Why? Because net force is 0, but net torque is not 0. So this is not a condition of equilibrium this time. Two conditions exist in 0 and 180. One is stable, one is unstable. Why is one stable? Because dipole is able to go back to its original position. And second one, when the dipole is not able to achieve its own position, which was the original position. Fine, that's all about torque, which you have to remember. Basic questions from this come. Tau is equal to P cross E. So you will write PE sine theta. Direct questions from this come. Then concept of electric field lines. Here, this is the very easiest topic. Here you have to just remember the property. These are continuous curves which are dropped by dropping a tangent on the electric field. So if this is electric field, you'll drop a tangent and get the electric field line. Continuous curves are there, and see, if two electric field lines will intersect among each other, what will happen at this point A? One direction is this and one direction is this. So at a single point only you're getting two directions, right? On a single point, this point is A, one single point. How can you have two directions of electric field? For that's why we never say two electric field lines cross each other. Fine, so two electric field lines never cross each other because at the point of intersection, two tangents cannot be drawn. And if two tangents are drawing, it means two different directions are there for electric field at that particular point, having same magnitude. So that is physically impossible. That's why we don't draw it. Then another property is that wherever electric field lines are kept closer to each other, like this, it indicates what? Stronger electric field. Wherever they are kept far away from each other, it indicates these are weaker electric field lines. This I have discussed with you. For positive charges, electric field lines move away. For negative charges, it will move towards it. So this is how you get a continuous diagram. And class, one of the easiest question is from electric field line. And chances are there that question can be asked to you. Questions are asked from this part. They are continuous curves, lateral compression. See, this is not very important. Mainly you had all these topics important. So these properties can be asked to you, or you can be asked to check whether it is correct or incorrect. Suppose if I draw suppose if I draw, and you have the other 4 figures are also there. You have to identify which one of them is wrong. Obviously, this is wrong. This is a positive charge. How can 2 lines be having opposite direction away from the charge? Fine. So this is this was about electric field lines. Then you have electric flux, one of the most important topics. And class, if you have lesser time left with you, I'll suggest directly start from Gauss theorem and electric flux only. Do not waste your time in other topics. Directly do electric flux and Gauss theorem only. So electric flux is what? This is basically number of field lines that are crossing area normally. Whatever lines are perpendicular to the surface, these are crossing the surface area normally, we term it as the electric field, electric flux or number of electric field lines. Right, so we have a formula ES cos theta or E dot S you can write. This is when you have to integrate it E dot ds. When it is non-uniform, for non-uniform you integrate it. Now see class. This is important. Gauss law direct statement can be asked to you. Gauss law says that electric flux, this is 1 over epsilon naught times the total charge that is enclosed. So according to Gauss law, electric flux through closed surfaces 1 by epsilon naught times the total charge that is enclosed by the surface. This is exactly what is meant by Gauss law. 4, 5 properties are also there. First property says that, see, here area wasn't used, radius wasn't used, simply charge and epsilon naught was used. So it means whatever be the shape of your material, flux is independent of it. Flux does not depend on it. And then only consider charge enclosed, means take the inside charges. If you have this system with you, no, consider these 3 only. Do not include these 2, 4 and 5. Just include 1, 2, 3. Why? Because these are not enclosed within the closed surface. Enclosed means you have to see whether the surface is closed or not. Then again, for positive charge, lines move away. For negative, lines move towards it. This we have seen. And yes, if theta is 90 electric field line, this will become 0. Why? Because they won't be crossing it within, they won't be perpendicular to it. Right? They are not actually perpendicular to it. And if you're talking about a dipole, net charge for dipole is 0. If net charge is 0, flux will also be 0. Then you have continuous charge distribution. In continuous charge distribution, 3 things are there. Just remember this in short. Charge per unit length is known as linear charge distribution, represented by lambda. So lambda will be Q by L. Then you have volumic charge distribution. You have linear, then you have superficial charge density. In superficial charge density, you have charge per unit area. So 1 dimension increases. Here it was only 1 dimension length. Now 1 more dimension increases to 2 dimension. That is length and length, that is area. So lambda is equal to Q by L. Then you have superficial charge sigma as Q by A. Here. Q by A or Q by S. This is surface charge density or superficial charge density. Both the names are right. Then finally, you have cubical charge distribution or volumic charge distribution, represented by rho, volume divided by a charge divided by volume. So charge per unit volume. Then these are the applications. These applications derivations can be asked. Any derivation of these are asked. Fine. So any specific topic, I'm again repeating, those who have joined late, you can take any topic which you want to revise, any topic which you are having difficulty issues, write it, mention it. I'll be taking it separately also on other weekdays also I can take. Now in the entire month that is left, you are having doubt classes. So just mention the topic on WhatsApp to me. I'll arrange a class for you. Whether it's theory part, if you're having difficulty in numericals, or whichever particular topic you have. Fine, let's practice some questions from here now. Asta, were you saying something?
No, ma'am.
Okay, okay. See here, electric field is given as 6 I cap plus 3 J cap plus 4 A cap, 4 K cap, 20 units in YZ plane. So we always take the perpendicular to it side. So see, YZ plane, this is your axis. If this is YZ plane, right, this is YZ plane. So perpendicular to it will be along x-axis. So electric field, you will write it as 6 I cap plus 3 J cap plus 4 K cap. Surface area, you will write it as 20 I cap. So flux will be EA, that will be 6 I cap plus 3 J cap plus 4 K cap multiplied by 2 I cap, 20 I cap. So you will be just having, see, these will be 0 because their coefficients are 0. So that will make 120 units because no unit is specified here. So we'll write 120 units. How we got I cap is that, see, when you are taking the flux EA cos theta, we write no flux is EA cos theta. So we take the perpendicular to the surface. This is known as N cap. And electric field, let's say electric field in some direction. This we take, we do not take with the plane. So here perpendicular will be towards x-axis. That's why we got 20 I cap. Yes, you have to start with this formula only, Fahad. Flux is equal to charge enclosed by epsilon naught. Get the value of flux, then only you'll be able to get the flux density. See, flux density means flux divided by area, total flux per unit area. So first you will calculate the flux. Flux is charge divided by epsilon naught. Q over epsilon naught, no? Q enclosed. Charge is given 17.7 into micro. So 10 to the power 6, 10 to the power minus 6 micro coulomb. And epsilon naught is 8.85 into 10 to the power minus 12. So see, you will get the answer. This will exactly be double, no? If you take, you can round it off and take it as double. So that will be approximately 2 into 10 to the power 6 Newton meter square per coulomb. Now, when you take the area, surface density, flux density. So see, flux density, this is equal to flux divided by area. So flux is 2 into 10 to the power 6. Area, what is given? Sphere, no? So area of sphere is 4 pi r square. This becomes 2 into 10 to the power minus 2 into 10 to the power 6. 4, 3.14, radius is 0.5 whole square. So that will also be 4.5 whole square. When it will go up, it will become 4. 4 will get cancelled. So this comes out to be 6.4 into 10 to the power 5 Newton per coulomb. This is the flux density. A circular plane sheet of radius 10 centimeter is placed in a uniform electric field of 5 into 10 to the power 5 Newton per coulomb, making an angle of 60 degree with the field. You have to find electric flux through the sheet. See, this is making an angle of 60 degree with the electric field. It means if this is the plane, this is electric field. This plane is making 60 degree with electric field. You consider the normal. You have to take this angle. This is 30 degree. So your answer, I think, Asta, that's why it isn't coming incorrect. You must have taken 60 degree. You have to take, yes, 30 degree. Because we have to take the angle between the normal area vector. This is the area vector that makes with the electric field. So flux will be EA cos theta. Electric field will be 5 into 10 to the power 5. Area is okay, 10 centimeter. It's given. Okay, circular plane sheet. It's there. So this will be circle, not rectangle. So pi r square we'll use. Yes, pi r square. Right. So pi r square we'll use 10 into 10 to the power minus 2 whole square into sine 30 cos 30 degree. This will be cos 30 degree. So when you solve, your final answer should be 1.36 into 10 to the power 4 Newton meter square per coulomb. 2-point charges, each of 5 microcoulomb, but opposite in sign. These are placed 4 centimeters apart. You have to calculate the electric field intensity at a point distant 4 centimeter from the midpoint on the axial line of a dipole. See here, the charge that is given is 5 into 10 to the power minus 6 coulomb. The separation between both the charges, this is 4 into 10 to the power minus 2 meter. Right, I'll write it 0.04 meter only. So here you'll have, when you will just talk about A, it will become 0.02 meter and R will be 0.4 meter. This is how we write it, because here you can directly see this is 4 centimeters, right? This is 4 centimeter. You have to calculate electric field intensity at a point distant 4 centimeter from midpoint. So this is 4 centimeter and this is 2 centimeter. So since nothing is mentioned, let's use the standard formula for axial field. This will be 2 kpr by r square minus a square to the power whole square. So 2 into 9 into 10 to the power 9. Dipole moment, see, charge multiplied by 2a. So 5 into 10 to the power minus 6, 2a is 0.04 divided by r square 0.04 whole square minus 0.02 whole square. Fine. So when you solve all these, you should get the answer as 10 to the power 8 Newton per coulomb. Just calculate and cross check whether it's which value it is coming. See how many electrons should be removed from a coin of mass 1.6 grams so that it may just float in an electric field of intensity 10 to the power 9 newtons per coulomb, which is directed upwards. This means this is a coin. Here you will be having the gravitational force mg. Electric field is directed upwards, so you have the electric force also upward as QE. Right. Electric field mass is given as 1.6 gram. You have we can write it as 1.6 into 10 to the power minus 3 kgs. Then you have electric field. This is 10 to the power 9 Newton per coulomb. So charge is equal to Ne. Right, charge is equal to Ne. And what is the force equal to? Force is equal to Q into E. So this becomes Ne into E. If you put it directly from here, this becomes Ne into E. This is the force. And one force is gravitational force. So we can equate this NEE is equal to mg. You just have to find out number of electrons. So N will be mg divided by E into electric field. Mass is 1.6 into 10 to the power minus 3. This is 10. This is 1.6 into 10 to the power minus 9. Electric field is 10 to the power 9. So how much? 1.6, 1.6 gets cancelled. This also gets cancelled. Or you can, if you write that, you'll write it as 10 to the power 8. This will approximately be 10 to the power 8 electrons. Fine. So N is equal to mg divided by EE, 1.6 into, right, 9. This will go up. This will 10 to the power minus 9. Minus 19 is there. This is minus 19 and minus 3. Right. So 10, 8. Just check if it's 10 to the power 8 or not. This should be around 10 to the power 8 only. Note down the solution and then text me done when you are done, when you've completed. All right, then those who have completed, you can leave. Tomorrow we'll complete the next lesson, that is of electrostatics, potential and capacitance. Fine. Thank you so much, guys.
Thank you, ma'am.
Ma'am, could you explain this question again?
See, in this question, electric field is upwards. So electric force is directed upwards, QE. Then you have gravitational force acting. Gravitational force acting, it is downwards. So mg becomes equal to QE. Both the forces are equal. So you can directly say QE is equal to mg. Now, Q is basically, we can write now the quantization of charge. Charge is integral multiple of n. So integral multiple of electronic charge. So we write Q